Now in this problem, we have to find the Taylor expansion of sin x at x is equals to pi by 6. Now, Taylor expansion in one dimensional, if f of x is any function at x is equals to a, is given by the formula f of x is equals to f of a plus f dash a into x minus a plus f double dash a by 2 factorial into x minus a whole square plus triple differentiation of f of a by 3 factorial into x minus a whole cube and so on. Somewhere nth term and so on again. Now here we have to find the Taylor expansion of sin x. So the value of f of x is sin x and we know the value of a, which is given as pi by 6. Now sin x will be equals to sin pi by 6 plus differentiation of sin at pi by 6 into x minus a, which is x minus pi by 6 plus double differentiation, that is d square by dx square into sin x at x is equals to pi by 6 into x minus a x minus pi by 6 whole square plus so on. If we simplify this expression, we'll get it as 1 by 2 plus root 3 by 2 into x minus pi by 6 minus 1 by 4 into x minus pi by 6 whole square plus so on, which is nothing but option 1. Now in this problem, I is given as integral over c cot of pi z by z minus I whole square, where c is the contour 4x square plus y square is equals to 2 in clockwise direction. Then we have to find the value of I. Now, in order to find the value of I, so first what we do is we'll find the residue of the given function. Now, residue of this function will be limit z tends to 1 d by dt of cos of cot of pi z, which is equals to minus pi by sin h square pi. Now, from Cauchy's residue theorem, I is nothing but 2 pi I into residue. We know that residue is nothing but minus pi by sin h square pi, which will be equals to minus pi square 2i by sin h square x, which is nothing but option D. In this problem, we have to find the principal value of minus r power I. Now the given complex number is minus I power I. Now in order to simplify this, first we'll convert this minus I into mod ampere form, which says that e power I theta is nothing but cos theta plus I sin theta. Now if I take theta as minus pi by 2, then this will become e power minus I pi by 2, and cos of minus pi by 2 is 0 plus I into sin of minus pi by 2 is minus 1. So e power minus pi by 2 can be written as minus I. So I'll replace this minus I with e power minus pi by 2 in minus I power I, which is e power minus I pi by 2 whole power I will be equals to e power minus I square into pi by 2, which can be written as e power pi by 2, which is nothing but the principal value of the given complex number. That is option B.
Maximum input signal frequency that can be used with a circuit is limited by. Okay, this is based on cathode ray oscilloscope, that is CRO. The maximum input signal frequency that will be used with the circuit is limited by vertical amplifier.
Question is, a unity feedback closed loop system has open loop transfer function g of s equals to 1 by s square and a proportional derivative controller gc of s in the forward path is equals to tp into 1 plus tds, where tp and td are positive adjustable parameters. Which one of the following statement is false regarding above unity feedback closed loop system? Comes to statement A, the system is always stable. See, in the forward path, we have added a proportional derivative control. Means it adds 0 to the open loop system. Means adding 0 improves the stability of the system. Means statement A is true. Comes to statement B. The system may have damped oscillations for the unit step input. See, if we take the closed loop transfer function, that is closed loop transfer function equals to g of s by 1 plus g of s h of s. H of s equals to 1, g of s equals to tp 1 plus td s divided by s square. If we find out the characteristic equation, that is 1 plus g of s into h of s, we will get a second order equation. Based upon the tb and td values, there is a possibility of getting a damped oscillations for the unit step input. Hence the statement B is also correct. But comes to statement C, that is the system amplifies the noise. Adding 0 means it, because the proportional derivative controller acts as a high pass filter, so there is a possibility of amplifying the noise too. So statement C is also correct. But comes to statement D, the system has 0 steady state error for unit parabolic input. The steady state error is defined as limit s tends to 0 s into r of s 1 plus g of s into h of s. If we substitute the corresponding values where r of s is the parabolic input, h of s equals to 1, g of s is mentioned in the above equation, then we will get this equation outcome as a finite value. But in the option D, specified as a 0. Hence, option D is the wrong statement regarding above closed loop feedback system. Hence, the option D is correct.